In this video, I want us to look at links that you need to understand between the algebraic equations of polynomials and their graphs. We're going to start with the quadratic as being one of the most simple types of polynomial. These are your 6 basic arrangements that you can have for a quadratic equation. And you should know from the quadratic formula that b squared minus 4ac is really important. In the quadratic formula, if that piece of algebra, b squared minus 4ac, works out as a positive number, then you have plus or minus the square root of that positive number, which always yields two results, the plus version or the minus version. And so these two curves here will result if b squared minus 4ac is greater than 0. If b squared minus 4ac is instead equal to 0, then you get plus or minus the square root of 0, plus or minus 0. And it doesn't make any difference whether you take the plus or the minus. And so you only get one x-intercept. If, on the other hand, b squared minus 4ac is negative, then you have plus or minus the square root of a negative number. And negative numbers cannot be square rooted. And so that talks about the situation where there are no x-intercepts. b squared minus 4ac is known as the discriminant because it helps us discriminate between these three situations. All of these are interesting, but I think this one here, this arrangement, is most interesting. Let's look at some possibilities. These curves come from algebra such as those where you expect to get two solutions. That might be this graph up at the top. If I wanted to make this, then I could stick a negative on the front and I would get something along these lines. This one, y equals x squared plus 4, perhaps, for this top one. It doesn't factorise, can't be solved. b squared minus 4ac is less than 0. There are no solutions if you set y equal to 0, if you're looking for x-intercepts. But these ones in the middle, this is when you have what is called a repeated root. In this first sort, we have two distinct roots, -3 and +2 perhaps. Here, we have two roots, but they're both the same. They're indistinct. So we talk about a repeated root, or if you want, just one root. Now this becomes an important idea when we look at cubics and higher powers, because the curve just touching the x-axis and then coming away from it again, the x-axis being a tangent to the curve, happens when you have this type of structure here. So let's take a look at a cubic and have a think about it for a moment. Suppose you had this curve here. Y equals x minus 2 bracket x minus 5 all squared. And remember, this could have been given to you in expanded form, and you would have used the factor theorem to find a factor. You would have then used algebraic division to factorize it fully. We would now be at this point and trying to interpret what it looks like. Okay, we can do quite a lot of this in our head. If we sketch this out, we know straight away that there's an x-intercept at +2 and another one at +5. In addition to that, the y-intercept happens when x equals 0. That is when we have -2 times -5 times -5. Now -5 times -5 is +25 times -2 gives me -50. We'll put that down there, -50. We can also see that we've got x times x squared. We're getting y equals x cubed. We're expecting a curve that either does that or that. One of those two will result. But these 3 points that I've marked on the graph, it's quite difficult to fit those into that shape. We can't quite judge what's going on. But if we recognize that here we have a repeated root, then at x equals 5, the curve will touch the x-axis, just like these ones up here. It'll touch the x-axis but not cut through the x-axis. Now how can that be arranged? Well, this curve must be coming up. It's got this shape. It must be coming up through here, like this, badly drawn. It must be coming up through here like this. It must dip back down, but we know that it doesn't go back through the x-axis because of this repeated root. So it comes down, it touches, and it takes off again. And so we've incorporated the basic shape, the x-intercept of 2, the repeated root at x equals 5, the y-intercept of -50. We've managed to include all of those features. But if we hadn't understood about repeated roots, then we'd have found it much more difficult to interpret this properly. There's one other thing to say, and that is the idea of the different powers in a polynomial. The highest power is the most important, and it might be odd or even. So we might have y equals mx, there's your straight line, mx plus c if you prefer, but specifically a power 1. You might have y equals ax squared plus bx plus c, so now the highest power is even. You might have y equals x cubed with some other algebra around it. You might have a quartic, y equals x to the power 4. Now, let's think about what happens. This is where you need to have a really good grasp of what happens with negative numbers and how they work together with positives. And hopefully you'll discover something that doesn't surprise you too much. Okay. You know as well as me that y equals mx plus c, if it's got a positive gradient, it just looks like that. It starts low and it finishes high. And again, you know perfectly well that if you have a quadratic, it tends to have this shape here. It starts high and finishes high. And a cubic starts low, perhaps has a wobble in the middle, and finishes high. Why is it that the odd powers start low and finish high? Why is it that the even powers start high and finish high? Because that's the sort of thing you might get for a quartic. Well, it's all about how negative x values over here on the left of each graph, how they work. If you have a negative value of x and you cube it, -2 cubed perhaps, then your -2 times -2 gives you a positive 4, but it's then multiplied by -2 again. When you have an odd power, it doesn't matter how high that power is, but there's always a stray value of x, negative value of x, on the end after you've paired up however many negative numbers. And so you always end up with positive times positive, finally times a stray negative. And this is why odd powers always start low. Once we're over to here, we've got positive numbers. You know that 2 cubed makes positive 8. So positive x values produce positive results. On the other hand, if you're squaring a negative number or raising a negative number to the power of 4, every pair of negative numbers in that multiplication, they pair up and there isn't a stray one on the end. And so you always end up with a positive result if you use a negative value of x. And so that explains the basic shape of these graphs. I could have drawn out y equals x to the 5, y equals x to the power 6. We would see the same thing happening. Now, in terms of how this all fits together with I've forgotten what I was going to say. Yes, sorry, beg your pardon. This wobble in the middle and this wobble in the middle. These only happen if you have extra terms, perhaps plus 3x squared minus 7x over here, x to the 4 plus x cubed minus x squared. Extra terms in the middle will produce these wobbles in the middle. But it's really quite complex how that works. It's worth your while going away and investigating it. It's particularly interesting in between x equals minus 1 and positive 1. The reason it's interesting in there is that if you have a small number like 0.2 and you cube it, it actually gets smaller rather than bigger. And so these effects tend to happen close to the origin. But that's perhaps for another video.